Hello, in this video I'm going to apply the Lagrange method to solve the firm's profit maximization problem in example 2.2. So, this is the firm's profit maximization problem, the total revenue, sales price times the quantity, less the total cost. And we're going to do it subject to the two constraints, the output constraints and the input constraints. To do Lagrange method, I'm going to rewrite the two constraints in the following format. 1 times C2 less than equal to 0, and I'm also going to move the maximum we can buy of the first input factor to the other side. Now we can construct a Lagrange function, which is simply the profit function itself less a Lagrange multiplier and our first constraint and the second Lagrange multiplier and our second constraint. And what we're going to do with this function is we're going to differentiate it with respect to all our 5 choice variables, and our original choice variables are Q1, C1 and C2, but we're also going to treat the Lagrange multipliers, the lambda 1 and lambda 2, as choice variables. What it essentially means is that we're also going to choose whether or not the firm wants the two constraints to be binding or not. We're going to use something called first order conditions, which is nothing but the partial derivation of our Lagrange function with respect to the one of the variables over here, and we set it equal to 0. Now, here are the first order conditions. The first one is simple. We have quantity over here and over here. Now, let's try to differentiate the Lagrange function with respect to C1. We have C1 over here, and here. And to make things easier, I want to rewrite this part to be lambda 1 times C1 times C2, and the last multiplication in the power of a half, which is exactly the same as taking the square root function. Now, the differentiation itself will become with C1 equals minus 5, and let's take the last one from here first, lambda 2, and plus this part, we have lambda 1, a half, so we're differentiating the outer function first, and in the power of minus a half now, and we multiply it with differentiating the inner function on this part with respect to C1 as well. And this would be C2 then. So now, if you set this equal to 0 and do some simplification, you would end up with first order condition number 2. Now we have the first order conditions. So how are we supposed to use them? Well, we need to solve this system of equations for the 5 unknown variables. The 5 unknown variables, our choice variables. So, first, notice that the first order condition tells us lambda 1 equals 40. Whenever we have a Lagrange multiplier that is above 0, we know that the constraint is binding. So we can write that quantity equals exactly the square root of C1 and C2. This should also be logical, because we know that the firms do not want to use more money on input factors than absolutely necessary, and the only way to do this is by not using more input factors than necessary. Okay. Then we can combine the first order condition 3 and 1, which will end up with having that in the optimum, and the asterisk or a star is always denoting the optimum. Combining these two conditions, we will find that in optimum C1 equals C2. So we use the equal amounts of both our input factors. And how we do that? We know from here that lambda 1 equals 40. So the first order condition number 3 becomes 40 times a half square root of C1 divided by C2 equals 20. So you have 20 over here and 20 over here. And you would end up with the square root of C1 equals square root of C2. And that can only be true given that we're assuming positive input factors choices when C1 equals C2. Now, next we can look at our first order condition number 2, and this would tell us that lambda 2 equals 15. So it is also positive. It would tell us that our second constraint is binding, so we have that the C1 in the optimum equals 15, the maximum we could use. But we already also know from here that the C2 in the optimum is going to be the same. So this part came from our knowledge what is our maximum input, or you can just go and look at the first order condition 5. I have left out some of the technical details. So the first order condition that tells us C1 equals 15, we have to verify that this actually applies, that we are on our capacity limit. In this case, that's true. And finally, we're going to use our knowledge that the output constraint is binding, that the quantity equals exactly the square root of our inputs multiplied together, or in other words, that Q in square equals C1 times C2. Well, that's exactly what our fourth first order condition tells us. So we have that the quantity square equals 15 times 15, which of course means that in the optimum the quantity is also 15. Plugging our results into the profit function, you will get that the profit is 225. Now a little bit about the multipliers. Lambda 1, the multiplier related to the first constraint, our output constraints, tells us how much the profit of the firm would increase if they could produce one more unit without increasing the input factor consumption. This is not surprising that it's 40, because 40 is the marginal revenue, or the price at which this extra unit can be sold at. Our second constraint, lambda 2, tells us that the firm's profit would increase with 15 if the firm, instead of buying 15 units of the first input factor, could acquire 16 units. So one more unit. However, interpreting where this 15 comes from is a little bit more difficult than interpreting where the lambda 1 equals 40 comes from. Because in the next case, the input choice, in this case, the choices, both the input as well as the output, can change. Bye now.